Okay, in chapter 2, we're gonna get into rectilinear motion. So so after chapter 1 and we come into chapter 2, we're gonna focus on something very important, okay? Your kinematics of particles. So don't let this word intimidate you because it's a big word. It's all about studying motion in a simple word, okay? Without worrying about the forces causing it. So it's like just the what, not the why. Yeah? I've taught you repeatedly kinematics is about what, and kinetics is about why. So specifically, we can break it down into rectilinear motion. So this one here, yeah. I think you can see the arrow here. Yep. And so this type of motion is the motion along a straight line because of this word linear. Yeah, rectilinear motion. It means the motion along a straight line. So think of it like understanding how something moves, whether is speeding up, slowing down, or staying constant or steady, okay? And it's all in a straight line, yeah? So what happened to my drawing kit here? Okay, I got my drawing kit. So anyways, it goes in a straight line or a straight path like that, okay? Of course, from chapter 1, we talked a little bit about the particle and the rigid bodies, yeah? So now we're going to get into particle versus rigid body kinematics. Basically, again, how things, yeah, because of this word, how things move. So rigid bodies, all right, they're just objects, and they can move. Everything moves anyway, so they can move, yeah. But we are not going to say just move anymore. We're going to use another word, okay? Types of movement, okay? Not just move, but how does it move? So rigid body, they move, particularly they translate and they rotate, okay? So now we have two different types of movement. The very first one is translation. The second one is rotation. Yeah, so rigid body can do both types of movement. Okay, so they can translate and then they can rotate. So when you look at this plane, okay, it can move forward. Yeah, if you think of an airplane, you know it can move forward. But it can also rotate, all right, along three axes that we learned from chapter 1. Yeah, your X, Y, and Z. They can roll, they can pitch, and then they can yaw. So when you count, all right, that you get all together 6 degrees of freedom, and we call it DOF is degrees of freedom. Okay, so that's 6 degrees of freedom because they can roll, pitch, and yaw along 3 axes, okay, which is gonna make it very complex to study. All right, so roll, yaw, and then pitch. We have 3 axes producing 6 degrees of freedom, right? Rolling is longitudinal on this axis, yawing is on the vertical axis, and pitching is on the lateral axis. Okay, all right, so on the other hand, we have particle. Yeah, so that's another type of object. We put all the objects in the world and universe or universes as far as we can understand into 2 big groups. Okay, so second group is your particles. They are, like I said in chapter 1, they're very small. Yeah, so these are simple objects, so they can only translate. Okay, here in chapter 1 we said, oh yeah, we're gonna consider its rotation for rigid body. For particle, it can only translate. Its size is negligible. Okay, and they're simpler. They're very, very simple, yeah, objects. So therefore, they have only 3 degrees of freedom. Why? Because it can only translate. So you got 3 degrees out of it, and here another 3 degrees of freedom out of it. If you can do translation and rotation like rigid bodies, you get 6 degrees of freedoms. If you can only do translation like simple particle, then you can do only 3 degrees of freedom. But for this course, okay, conceptual dynamic, we're gonna make it even easier for you. Why? Because we're gonna look at just 1 degree of freedom. Okay, it means we're gonna do only rectilinear motion, the motion in a straight line. Yeah, very complex, relatively complex. 1 degree of freedom is basic. Yeah, easy. Easy enough, of course, because there's only a straight line motion to start with. Alright, so this is kind of like a review, yeah? So we're gonna break down a particle rectilinear motion by starting with a very simple question, yeah, making you think. So what is a particle? So like we study in chapter 1, yeah, a particle is basically something with mass, right? But no size. So imagine a small point, yeah, that represents an object mass, yeah, like a marble or even a planet. Except we're not worried about how big it is or what shape it has. Okay, all we care about is how it moves. So particle can only translate, all right? So when we study particle, we're only looking at translation. And that's a type of movement, okay, in the space, okay? There is no spinning, there is no rotation. All we care about is this translation, okay, the movement, straight line movement, okay? why do we do that is when we study it simplifies, right, things a lot. And that's why the motion in a straight line, your rectilinear motion, is a great starting point for understanding kinematics. Okay, and that's the reason why we start from 1 degree of freedom with a tiny little simple mass without size, because there is no size for very, very small tiny little particle. Okay, it has only mass. Even though we loosely say, oh, the size is small, the size is small for the particle, mathematically we have no size. Okay, all we have is mass. Okay, for the particle that we are considering to study. And of course, we have to mention this again and again, yeah, when we teach dynamics, is because students always go into confusion about the particle because of the common word that we use outside. So a lot of people say, like, oh, the photon, the size of the photon is very small, the size of the electron is very small, right? When we go to high school observation, the science teacher or whoever teaching the engineering, right, class, they would say like the particle size is so small, electron size is so small. No, the particle has only mass. Even though we identify it, or we commonly use the word, right, is size. The electron size, right, is okay, about 10 to the power, right, minus 20 something, like small. So anyway, in dynamics, again, the particle has only mass, okay, no size, because it's so small. And of course, when we study translation, okay, you got to be very, very careful, right, not to miss this, all right, fact. And the other one is it cannot rotate. Your particle cannot rotate. It's just plain straight translation. And out of the translation in 3 axes, okay, we're gonna just do 1 degree of freedom, okay, in this course. All right, so don't forget this very, very important aspect of this course. Okay, so now we know what a particle is. Yeah, you must be very confident about particle, and we're gonna get into rectilinear motion. So what is it? It is a motion. Yeah, it's a movement, and this motion is happening along a straight line. Yeah, simple as that. And of course I wrote it here 1D. So this means one dimensional motion. Okay, so meaning we only need one axis, just single axis. We always have 3 axes, okay, your x, y, z. Out of that 3, we're going to consider only one axis in this motion, okay, like a number line to describe that. Every time we have x's, we have some equally distant mark on it, right? Every time we analyze the motion, and because that's how we measure. It's like a number line to describe the axis. So for example, think about a car. Think about a car driving. So this is car driving straight down a road. Going straight down a road. Or you can imagine an elevator. That's also another good example. Going up and down Yeah, moving up, moving down. There is no turning, okay? No turning, no rotation, no curving, okay? Involved in this type of motion. Just very simple back and forth along a single path, okay? A single straight line. As simple as that. And if you can understand the motion on one single axis, one-dimensional motion, then we can use that knowledge to be able to understand, okay, three-dimensional and complex rotation, all right, and more complex, all right, movements or motion. We always have to start with the very basic, yeah? So this is your foundation for understanding more complex movements. All right, so here is a diagram, to see the coordinate axis. We have only a single axis, and because we call that rectilinear coordinate axis, right? So you can visualize here. So we've got a straight line, and in this example, of course, I'm calling it s-axis. And this is your particle here, yeah? And it is moving along s-axis. And we call this one the particle's path, right? And so I'm going to write it here, particle's path. Alright, and here when you look at this point, see that? And that is the origin, yeah? We mark it, its symbol is O. And that's our starting point, reference point, where we start to measure the distance, right, of the particle on that s-axis. So it's like the zero on that number line. We're imagining the path this particle took, like a straight line, and we mark it 0 as a starting point. Yeah, without the starting point, again, without the starting point, is very difficult for us to measure. Yeah. So now we have the starting point, so we can easily measure how far this particle moves. Okay, so the distance traveled, meaning this particle has traveled from here to here. First position, suppose it begins from here, we give it 0, we start this, distance is 0, moving, all right, to the right. And of course, since I call this path as s-axis, okay, the distance traveled is going to be written or represented by s. Okay, so your distance travel is s from here all the way to here. Okay, where it starts and where it ends. So it's moving to the right, and we give it positive direction. Okay, and that means you're going in that direction, one direction. Moving to the left, mathematically, we just put it like negative, right? Negative means going to the opposite direction. So this coordinate axis is going to keep things simple for us, yeah? Because everything happens along one dimension on one single axis. Okay, so you have only 1 degree of freedom. And every time we try to solve rectilinear coordinate axis problem in your head, okay, in your mind, you've got to keep this diagram, all right, picture, so you know what you're doing, okay? All right, on the same coordinate axis, we have only one, s-axis. You need to know another, okay, dynamic term, and that is position, yeah? So what is position? Well, position is gonna tell you where your particle is located, all right, on that coordinate axis. Here in our example, we call it s-axis. So think of it like dropping a pin, all right, a pin on a map. So it's going to show you exactly where your particle is, yeah, on this coordinate system. So this is the particle's final position, yeah, and this was its initial position, okay? So in this diagram, the particle position is we're gonna measure, yeah, like I have explained it to you, from this origin, yeah, and I call this a reference point, and it is at 0. In mathematics, we always give the 0. 0 means empty of, right? Empty of, and there's nothing. So if we think about number line, no number here, nothing to count, yeah? As soon as you take distance, yeah, far away from the 0, you start to have some number, right? Your decimal. And when you hit 1, you got 1, not empty anymore, yeah? So 0 is absence of something, absent of whatever you are interested in. On this line, we mark it with numbers. We call the coordinate axis number line for measurement purpose, right? So at this point, there is no number. At this point, there is absence of number, okay? Empty. And that is our reference point. It is 0. And the value of s, okay, all the number on this axis, okay, I'm just going to make it like 3 marks away here. Of course, you can make any kind of unit for this example. So the value of s is gonna tell you how far the particle is from this origin. Positive, again to the right, mean it is to the right, to the positive, and there is the value. And if you go to the opposite direction, yeah, from your positive, then you get negative. So negative s means it's to the left. So why position is so important? So knowing the position is super important, because it is your foundation for describing this motion. Without the position, yeah, you wouldn't know where things are starting from, or where they are going. Okay, so therefore position must be defined for us to locate the things. Okay, we in science, right, we try to locate ourselves. It's a piece of cake for now to locate where we are, yeah, on our planet. We have GPS and everything, so we can pin where we are on the map digitally, of course. We have satellites, more precise, yeah, in some country we have more precise location that we can pin ourselves. where our things are, where's my car, right? You can pin and find it with your phone, with your cell phone. Of course, when you go out to moon or something, up to the moon we can still pin, yeah. In the galaxy, solar system, there you lose your precision, yeah, because it's too big for you. Then you come into your own body, or in the plant's body, or in the animal body, yeah, in the material, and we try to understand the material in different bodies. Then we lose also accuracy in locating, yeah, the position. As you know, in science, we're not studying a single particle on a straight line. You're studying so many, yeah, objects, you included, everything on the planet and beyond. Try to locate to get this position, yeah. Of course, with the measurement system that we know, yeah, human knowledge. So therefore, the measurement system is limited to our human intelligence. Okay, so anyway, come back to science and engineering here. You need to know position. Okay, why? It's because it's going to tell you starting, yeah, point and current, yeah, current point. All right, and we're gonna go into position a little more details, yeah. So position doesn't just tell us where a particle is in dynamics, yeah, because it also has a direction, yeah. So this means that it has magnitude. So the magnitude in this example, because we are our interest is distant travel, so from here to here, yeah, s, so that's your magnitude. So it means how far from here, starting point, to the final point. Okay, so this means it has both magnitude, how far, and the direction is going to the positive, okay, to the right. All right, so this is right side and that is left side. So you have two directions on this coordinate axis, yeah. So here is the question that you have to think about: is position, yeah, in dynamics a vector or a scalar? So let's review the vector and scalar. So scalar is, you know, just the magnitude, yeah, how far, of course in this example, how far it is. The vector is how far it is and where it is going, all right? So technically, position is a vector, yeah, because it includes the direction, yeah. But to keep things simple here, yeah, for now, for you, we're gonna skip the vector arrows, yeah. We usually use something like that for vector. So we're gonna skip the arrows for now, and we're gonna use the positive and negative values for your direction. Okay, so this little particle is going to the positive direction. So on this s-axis, if s is positive, the particle is going to the right. Okay. And if s is negative, the particle is going to the left of this coordinate axis. Okay, so we call this right because it is on your right hand side. Okay, and then we call this left because it is on the left hand side when you are looking at that coordinate axis, when you are looking at it. Okay. We always teach dynamics with one axis for your foundation. so you can be able to, all right, transfer that one axis knowledge to two other axes, okay? So that way you can be able to understand more complex motion, okay? This is a very basic and very simple motion for you. All right, another dynamic term is displacement. Okay, so now you have three. Yeah, the very first one is position, and then we did distance traveled, and now is your displacement. And you need to know, yeah, the difference between position and the displacement. So these are two terms. They sound similar, but they have different meanings, okay? And they, of course, they mean different things. So position, as we have just talked about, is going to tell you where a particle is at any given moment. Okay, we're just imagining it was here on that coordinate system that we have constructed. Okay, 1D, one-dimensional coordinate systems. So, for example, if let's say like if this particle is about five meters, yeah, we're gonna make it up a distance, yeah, five hypothetical, yeah, meters. So 5 meters to the right, that's your positive, yeah, to the right. Right of what? Right of your reference point. So your reference point is your 0 here, origin, okay? So the origin, a big O number, little 0, going to go from there all the way to here, and you got 5 meters. Yeah, you have 5 meters distance traveled, the position the particle took a new position right there. It was right here, yeah, previous position, current position, and it is, okay, to the right side of the reference point. So that's positive, on the positive side of this coordinate axis. So its position is, I'm going to precisely define it. It is at positive 5 meter away from the origin. Okay, now displacement, so that's about the change. We're now concentrating not only position but the change in the position. Okay, so displacement, we usually write change like that. Okay, little tiny triangle symbol. So every time you see that, you know you are dealing with change. Okay, it's like change in position is your displacement. So it's like asking how far has the particle moved from where it started, yeah, from here. So to calculate your displacement, yeah, displacement of this particle in this example, you will have to subtract the starting point, yeah, as we call it initial, yeah, initial position. So as initial from the final position, because this is your final position, yeah, as a final. So here we, in this example, we start, okay, here, and then the final position is here, yeah. We are measuring the distance from the reference point, your origin, to here, and then you measure from here to here. So we have initial position and then we have final position. Okay, so the displacement is this guy. See the change. Okay, and mathematically we define that change in this way. Okay, put it in a math equation. So the change in position, which is displacement of this particle, in this interval, of course, is your final position minus initial position. Okay, so if you put it, we know that we are on s-axis, where on s-axis we're at final point, and we were at initial point, so you're gonna subtract initial position from final position, and that's how you mathematically calculate this, all right, distance, which is the change in position, and we call it a displacement of that particle, right? So in order for you to calculate the displacement, you gotta find where did I start and where did I end, okay? So displacement again has direction. See this arrow showing you going to positive, side of your reference point, and a negative, of course, displacement, okay, means it moved to the other side, here, move to the left. So the next thing that you need to know is total, okay, distance traveled. You gotta understand the difference between displacement and total distance traveled. Displacement, we have just learned, is a straight line difference between where you started, your S initial, and where you ended up, your S final. And you know that it only cares about the change, the net change in position of that particle, and not the path that it takes to get there, but for total distance traveled, all right, it's going to measure the entire path, that particle took. So for example, like you can imagine walking in a zigzag line. What happened to my drawing? So if you walk like that, ding 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 ding, okay, so let's just say like going from this point and you walk all the way to this point and you end, so where you start right here, and then where you're gonna end is here, your displacement, you start and then you end. It's gonna take a look at only that, all right, change. But you couldn't have actually walk about, let's say from here to here, if you measure it, let's say we have only like 5 meters, 5 meters. But if you go in a zigzag like that, right, wiggly way, you're gonna have more than 5 meters. Okay, you will be traveling more than 5 meters, even though you started from the same position and you ended up, at the same final position. So because this is short, a very very short, exact from here to here that you go straight, and here is that you're going, around like that and get there. So you couldn't have actually walk 5 meters, total, if you go this way. If you took this path, see this path, the pattern of this path is different from this, because this is completely straight line and that one is going wiggly, So total distance traveled is that. Yeah. So the total distance traveled from here to here on the path 1. Okay. I'm going to write down here the path 1. And the total distance traveled by taking this path 2. Okay. They're different. Yeah, they're different in distance. So this is more than 5 meters. You would spend more than 5 meters on this path, and you would spend about 5 meters on this straight line. So it's shorter apart than that. Okay, so we usually call on the map as just shortcut, and that's going a long way. If you call the direction in your GPS, maps or Google Map or whatever GPS navigation you're using, it's going to give you a different path. About 3 suggestions you're going to get. Well, if you go from here to here, that's the shortest. If you go from here to here, taking, like instead of highway, you're taking a town road or something, going through city, then it's going to take more time, and more distance to get to the same destination, like that. Okay, so that's your total distance traveled. So now here is the key. So this is just giving you a link to our interactive textbook workbook site. I'm taking you there. So here you're gonna get a diagram, showing you your position, your displacement, and your total distance travel here. Of course, this is a systematic diagram, so when you take a look at it, you wouldn't understand like my wiggly drawing. So this is actually easier for you to be able to understand, because if you're taking longer path, then this is shorter, and total distance traveled. Okay, and if you're just looking at the change, initial position and the final position, it doesn't include the path. If you include the path, and then that's your total distance traveled. So the displacement of a particle and its total distance traveled are only the same, okay, when the particle does not turn. So say in our former diagram, see, it turns second time, third time, fourth, fifth, sixth, seven, 8, and 9. No turn, straight down. Straight going from this point to here. So that's what we're saying. So they will have the same, okay, the same distance when the particle doesn't turn. But if the particle turns, alright, if the particle does turn, then it will have different, okay, total distance, travel distance, and you have a displacement value and the total distance, travel value. Even though their distance values, they're going to be very different. And that's what we're talking about. Of course, if we go with the formally written text, then you have issue understanding it. So make sure you draw your own diagram to be able to understand, right, these two dynamics term. That's displacement and total distance traveled. Okay, so the key is the displacement and the total distance traveled are the same when the motion happens in a straight line, okay, without changing the direction, meaning there's no turns. So if you turn around at a point, total distance is going to be always greater than your displacement. Okay, so now I want you to carefully look at this. Starting point here, end point here, okay, change in position 1, position 2. The change in delta S, we call this little triangle delta. It's a little tiny triangle. So the change in the position from here to here, yes, is that much. Okay, now we can draw it here. Yeah, it starts here and then it ends up there. No turn, straight. So therefore the total distance traveled is the same as your displacement. Okay, now you're gonna start here. Yeah, another, all right, the position. So we're gonna start from here. Yeah, depends on the dashed line. So see, starting point here is the first position, and then your end position is there. Yeah, start position, end position. So going to the negative side. So you go from here to the bang. The change is the same, delta S. Okay, see that? Just going to the left. Okay, now you're going to start from here for total distance trouble, and you go there, all right, the position here, and then you turn around and you go past the initial point and go to the left, and then you end up at the same position. Okay, so here, see that how the particle has taken a longer path, yeah, but ended up at the same final position. Yeah, so going from here to here, bang, that's delta S, okay, to the negative position, which is this way. Yeah, and that is your displacement going to the negative direction. Your total distance travel is like this. Okay, S1, see, because this amount of distance is S1, you go there and you turn and you travel S2 from here all the way to here is S2, and then you ended up at the same position as in displacement. Okay, and the entire path S1 plus S2 is your S total, and that is your total distance traveled. Yeah, distance along the dash line. Okay, I think you got it, and I want you to study this diagram very carefully. Okay, of course we're going to come back here and then I'm going to show you a bigger diagram, which is the same diagram from our interactive, yeah, our website. So now you can see the diagram a little bit bigger. So if you want to review it, the difference between the displacement and total distance travel, they're different. Yeah, first thing you have to know this diagram. Again, I am teaching you very slowly. It's because I want you to get it. Okay, I really want you to get it. So the particle starts at S initial. Okay, right here. The diagram, almost all of the physics or engineering, okay, diagrams are a little bit tricky. So you might think like the starting point is here. No, that's the reference point. Okay, the starting point depends on your problem. Yeah, so in this particular problem, the path, is the starting point is from here. Yeah, and of course you have another one, and then you have another one here. Yeah, and another problem again, your starting point is here. In the third problem, your starting point is here. So you've got to carefully look at the diagram and see like what starting point am I dealing with. Yeah. So in this particular problem on this slide, from the previous slide, of course, we're talking about the starting point is this middle guy. Okay. So that's where we're starting. So the particle starts at your S initial, yeah, which is this. And when you look at it, I don't know why, like some of the students have issue, they usually think that the starting point is here, yeah. But no, this is just telling you the value of that, the position. Okay, so when we say like S initial, meaning the starting point is here, but the value is, this is, let's say, I'm just going to make it up, this is 3 meters away from the reference point, 5 meters away, and this, let's say, like 10 meters away from the reference point from this, okay? Here and then here and then here, yeah? Because coordinate axis is a number line, yeah? So that's what it's talking about. So this position, yeah, S final is only 3 meters away from the reference point, which is your origin, okay? So be very careful when you read the problem, yeah? So you're going to start from here, but the value of that position is 5 meters, yeah? And you're going to start and move along, yeah, the dash path, and then you're going to end up here at the end of the arrowhead of the dash line, yeah, the dash path. So that's your S final. See, the S final is only 3 meters. Initial is 5 meters away from the origin. Final is 3 meters away from the origin. See, like how it tricks your mind. I started 5 meter position, okay, on the coordinate axis. I ended up at 3 meter position on the coordinate axis, okay? So you can travel. So you know that since you end up at the lower number, you know that you're, like reducing, yeah? Reducing, meaning like as soon as you see going from 5 to 3, you know that you're going to the negative direction, yeah? Because this way. And you are facing towards the origin, okay? And of course you have taken 2 meters, yeah, in displacement, because it's only 2 meters from here to here anyway. But when you think about the total distance traveled, because you have taken an extra path, you're not only 2, you have gone from here to here, so that's another 5 meters, yeah? So from here to here, that's 5, that's 10, so that's 5, yeah? So 5 you go, and then you go 5 more, and then you have 2 more. So altogether 5, 5, 10, and 2, 12 meters. You have total distance traveled. You only have 2 meters if you have taken without turn straight line from here to this initial position to the final position. If you have taken this longer path, go that way, turn, come back, pass the initial point, go to the end point, yeah, you would have traveled 12 meters in total. Okay, so the key point again, don't forget, yeah, your S total is what in this example, S1 plus S2. S1 is 5, S2 is 5 plus 2, so altogether 12. So the key point is if the particle moves in a straight line without reversing direction or turning, the displacement and the total distance traveled are the same. But if it changes direction, like in this case, okay, see, turn and then reverse, the total distance traveled will always be greater than the displacement. Okay? Study this and try to get the difference of that. Of course, in a multiple choice question in your quiz or in your exam, in your test, okay, is going to be worded. So you're going to try to refresh your memory about this diagram. Yeah? Of course, then we come here and we're gonna do this exercise, okay? And this is actually your in-class assignment, okay? In my very first lecture for chapter 1, all right, I explained everything for you. But you will listen to the lecture, and I will tell you exactly how we do the things, right? And when you come to the classroom, you're gonna have to redo this, okay? So make sure you actually understand it without memorizing, okay, the answers. So try to understand, like how to solve the problems. So here the problem is you have to rank, yeah, the groups. So you're given 1, 2, 3, 4, 5, 6 of them, yeah. And you have to rank the groups from greatest to least amount of particle, yeah. Displacement over the time, right, interval from 0 to 3 seconds, okay. I already give you your digital workbook, yeah. So it's going to be right here, rectilinear motion, conceptual example 2.1-1 in your, of course, lecture handout. See, this is the same example that you have to look for in your workbook. So conceptual example 2.1-1, okay. So you're going to rank the groups, so that's our problem, okay. So when you take a look at it, the very first thing you really need to know is how to read it. Okay, so you're dealing with S versus T graph. Okay, T is for time and S is your position. Okay, and we're very familiar of reading, yeah, position as a horizontal line like that, but now your position is on the vertical line, okay? So it is 0 here, you go 10, and then you go 20. You can make it meters or feet, it doesn't matter what the unit is. You go 0, 10 units, and then 20 units. So that's your position, okay? So when you read the position against, all right, the time, when you look at it, it's set at 0 minute. Sorry, this is, you can make it second or minute, doesn't matter because there's no unit defined. Oh, actually, time unit is defined here. Sorry. So this is time is in second. Okay. So the time unit has been defined by your problem. So so let me erase this for some clarity, right? So that way you're not gonna confuse. This is not horizontal. Okay. So anyway, when you read this graph, you know that, all right, your graph A is at 20. That's what it said. Okay. So your graph A is 20. So the amount of particle displacement over time interval from 0, again, time interval. Every time you have an interval, you have a starting point. Okay, that's your reference point 1 and a reference point 2. Yeah, 0 to 3. So 0 to 3, what's going on? There is a particle, that's your object. And we're going to see activity. Your activity is a movement of the particle. Yeah, is happening. So one activity, the movement of a particle, happened between 0 to 3 seconds, yeah, of that time interval. What it does is when you actually look at it, it is at 20 unit in displacement, meaning the particle is at 20, okay, all 3 seconds, yeah. Now here the second particle is at 10, all 3 seconds. The third particle here is at 20 at 0 second. When I get to 1 second, all right, it is between 10 to 20, yeah. So if that was meter at 20 meter, and then I go down to about, let's say, 18 at 1 second. When we get to 2 seconds, the particle is already at about 8, okay, meters, and 0 meters. So the particle, right, started from 20 meter and then get to 0 meter, yeah, at the third second. See, that's how we read it. And here this particle is start from 0, 1 second, going to about 5 meters, 2 seconds, let's say, 12 meters, and get to 20 meters at 3 seconds. Yeah. This is going to the negative direction if we were to put the particle on the coordinate axis. That is going to the positive direction because it's taking, bigger units in the position line. So here the same thing at 0 second at 10 meter ended up at 20 meters at 3 seconds. Okay, start at 0, go to 20 at 1.8 second. At 3 seconds, go back to the 0, okay, meter position. All right, so that's how you look at it. So the question is rank it, rank them greatest, and we're dealing with the displacement. So the greatest is we have 0, 10, and 20. So the greatest displacement, what is it going to be? Okay, it's got to be displacement. The displacement, again, your definition of your displacement is you have the initial, okay, and then final. And your displacement is the change of the position, and you have to take initial out of final. That is your displacement. Okay, so you gotta find where's my initial at 0 and where's my initial at 3. So here the displacement is 0 there because there's really no change in it. Okay, and when you look at it, the displacement, look at this, is also 0 because there's no change in it. And when you get to here, the displacement, you start initial 0, the final 0, so your displacement is also 0 here, no change in it. Here when you look at it, you start 20 and you ended up 0. So your starting point initial is 20, your end point, okay, your final is 0. So therefore this is minus 20. Okay, 20 is direction and 20 is value, magnitude, and negative is your vector direction. And your D here, when you look at it, starting point is 0, ended up 20. So your start initial is 0, okay, which is this guy, and your final is 20. So therefore going to the positive direction. Okay, and your E, you're going to start from 10, okay, here, and you're going to end it up 20. So 20 minus 10 is going to be 10, and it is going to the positive direction. So if you were to rank it, you're going to rank, of course, C and D at 20. Direction doesn't matter because we're just looking at the displacement magnitude. Okay, so therefore they both are at 20 meters. Doesn't matter on that side or this side of your reference point or the origin. Okay, you still have the value, which is your magnitude. So therefore C and D, okay, we're going to rank it the largest change in position, and the second one is going to be E, because it has 10 meter. The change, delta S, the change in position is 10 meter, so therefore that's the second. And then you're going to rank the rest of them, they're all 0, so A, B, and F. Alright, and of course I gave you the answer in your slide, so you can check your calculations and reasoning. Okay, so this is the greatest, second, and then the rest. Then we come to the next one. Alright, the second part of the same problem, conceptual example 2.1-1. Now we are going to concentrate on the total distance traveled. we're going to do the same thing. The problem wants you to rank it from greatest to the least amount. But this time it's not displacement. This time it is the distance of your path taken. Yeah, so that's your total distance traveled. The same interval 0 to 3 seconds. Okay, so now even though it is s, we're now going to take a look at the path. Yeah, the path. So I'm going to write that down. Not the change. Displacement is the change. Now we're going to do the path. So the path is, yeah, if you remember the formula, you have to add everything, yeah, or every distance that it takes. So the very first one, okay, when you look at it, it is at 20, yeah, 20, but it doesn't move. Why? Because at 0 it is 20, 1 second 20, 2 second 20, and 3 seconds still at 20. Yeah, it means 20 is not the amount, it is the position. So here there is no change in position. Yeah, so therefore there is no distance traveled. Yes, because position is the particles stay at the same point. Here the same thing, look at that, the particles stay at the same point. Yeah, so therefore your A and B is, we're going to rank it at the lowest. Yeah, so the least amount of this total distance travel is these two guys. Then when you get to C, yeah, it has a substantial increase in position, because look at that, position started 20 and then 10 and then 0. Yeah, so therefore it has traveled, yeah, 20 to 0. That's altogether 20, yeah, total distance traveled. Then D, we can see the substantial increase too. Yeah, 0 to 20. So that's this distance traveled, 20 meters in total they travel C and D. Definitely more than A and B, which is 0 here. Yeah, and it is up there. Okay, so therefore I'm going to just, without ranking, I'm going to just put my calculation here for a while. Then I'm going to take a look at E, start 10, ended up 20. So the total distance traveled for E is 10. Yeah. For F, it starts 0, travel to 20. Yeah. And then it start 20, travels back, reverse direction 20. So altogether, this guy has traveled, since you have to add all the path, is traveled 40. Yeah. So it has total distance traveled 40 meters. If I were to give this unit a meter, yeah. So now we see everything very, very clearly, yeah. See how easy it is? All I look for is the path taken. No path has taken, no path has taken, therefore the lowest. Rank it down. Highest is your F, because it has total distance traveled of 40 units. Okay. Second is C, 20 units total distance traveled, and D, they tie. And then E, okay, because it has 10 units total distance traveled. So that's how you're gonna rank it. Yeah, the greatest is here, the least amount of total distance traveled is right there. Okay, it's not that bad. Yeah, so anyway, okay, Alright, so what I'm going to do is I'm going to stop right here because the next section is velocity, okay? And I'm going to go and eat, okay, dinner, and then come back here and I'm going to record another video for you on velocity.